Problem number 5. All right, here we go. Determine the value of the ratio of EGB to EGA. I like how everybody got mad about this. What's a ratio? I can't do this. But you're all haters. I knew you could do this. So just to keep that in mind, I'm actually going to work on this problem here. So we have two different spheres. We have B and A. And all that's happening is that they fall and they almost hit the ground. Okay. So sphere A starts off at 10 meters. And then it races towards the ground and gets all kinetic energy. Same as sphere B. Don't get all worried about it. You know what to do. So first, let's get the ratio of EGB to EGA. So EGB, let's actually look at the picture. We've got a 1 kilogram mass. We can say 1 times 10, and the height of B is 20. And then EGA, similar idea. That's going to be 1 times 10 times 10. And when we actually calculate this out, this is going to be 200 joules. This is going to be 100 joules. Don't even worry. You know how to divide. Just take this ratio, 200 divided by 100, and that'll be 2. I saw a lot of people say 2 to 1. That's awesome. I'll put this out there. If you put 200 to 100, I'm not going to give you a huge problem about it, but you know better than that. You've done ratios long enough that I would really want to see this reduced to the 2 to 1 ratio. Okay. Now, the next thing we want to do is we want to determine the value of the ratio of VB to VA just before each reaches the ground. So now we can use our energy conservation. So I know EG equals EK. And let's do that for each one. So for B, we've already got 200 is 1/2 times 1 times V squared. And when I isolate V, I'll end up getting 20 meters per second. That's cool. And then when I do the same thing for the second sphere, sphere A, that's 100 equals 1/2 times 1 times V squared. And that's going to give me a V equal to about 14 meters per second. Now, for those of you that really like math, you can show that the ratio of the speeds VB to VA is the square root of 2, but I'm not going to do that. Instead, when we take VB over VA, what you'll end up getting is about 1.4. Let me try that. VB to VA is 1.4. Awesome. So that's problem number 5. Let's take a look at problem number 6. All right, now here we've got the same mass. No, we have different masses. Sphere B is 2 kilograms. Uh-oh. Scary. And sphere A is 1 kilogram. And again, we can do the same thing with these bar charts. Nice. So again, no need to make it dramatic. Let's just keep it simple. So we got EG of B is going to be, what is that? 2 kilograms times 10 times a height of 20. Exciting. 400 joules. And then when we calculate the gravitational energy of sphere A, same idea. 1 times 10 times 10. And we're going to end up getting here 100 joules of energy. That's nice. Okay. So we get a 2 to 1 ratio. Now let's compare the speeds. Here's the interesting thing. I'm actually going to do part C first. The acceleration of B, how does it compare? It's the same because they're both g, negative 10 meters per second squared. It's gravity. Because it makes it fall. Gosh. That's right. Right. That's right. Shout out to gravity for holding it down. You like that joke? Okay. I think I might have said that before. Never mind. All right, now B. All right, VB to VA, let's just do that. So we got 100 joules. Let's just do both of these. We actually see here 400 joules equals 1/2 times 2 times V squared versus 200 joules equals 1/2 times v squared. When we do our math, is that right? 1 times 2, 20, that's 200, yeah, it's 200 joules here, so we got a 2-to-1 ratio. Okay. So we end up getting 20 meters per second for each speed. So we do get a 1-to-1 ratio. But it actually turns out that's because they're both subject to falling due to gravity. That's how we're getting that 1-to-1 ratio in a different way. In other words, you could have actually done this problem before you knew what energy was. So that's problems number 5 and 6.